Boys, it is Ghidra time. Like I threatened before, we're going to be doing a little bit of static disassembly and analysis because we don't want to look at, traces and just the debugger window all the time. We want to kind of build up our notes of what's going on. So static disassembly is going to help us do that. I've run around with this a little bit. I've played with this software just a tiny wee bit. It's from the NSA, so your privacy is not guaranteed, but that's fine. They can look at my ball picks. That's fine. Anyways, file, new project. Here we go. So we're going to call this one Wotes. Finish that. And then we want to import. So we could just copy this over to Ghidra. And we could just import this from, as a binary. We got to tell it what this is. It is 6800 code. We can now analyze this and it'll basically comb through all the bytes in here and try to find instructions using a bunch of heuristics. Try to find where the instructions are versus where the data is. It's tricky. You can't just, disassemble the bytes willy-nilly, because if you start at the wrong address, you're going to be, misaligned, and then you're just going to get garbage. So I think it probably uses a bunch of smart heuristics to find where the actual code is and where it starts and everything. So that being said, let's do a little bit of verification. I have my trace, and so I've got like addresses here where I know which instructions are at them because we actually executed them through the emulator. So we can verify that the same stuff exists in our static disassembly. So for example, 5EC8 is the address, if you remember, where gamepad button was pressed. That's the divergent address. So if I hit G and go to 5EC8, I should see the same code, which I do. We have load effective address here. It is created a label DAT, but the label's address is 5FC2, and that's what's happening here, loading it into A0. So this stuff is all above board, and I'm sure the rest of it is fine. I don't have to check it. Famous last words, but whatever. So if we scroll up here a little bit, we can find out where it actually loads the data from the gamepad itself, from the hardware. And that is B932, which is quite distant from this, so it's a different routine for sure. B932, let's go there. B932. And you can see here that it is, here's the function. So this function is probably where it's polling the gamepads. It's going to load the address here for gamepad 1, and then it is going to call the function B93, which is this one here. So it calls this function, which is really close, after loading the address of the gamepad. And once it returns here, it's going to load the address for the second gamepad. This function is actually inside of this function. They're not separate. And you can tell that because the first call here is a branch to subroutine. The second time it goes into this function, it doesn't actually branch. It just lets it fall through into this function. So it's like a weird function tacked onto another function where it's called itself once and then it just falls into itself the second time. And some of these do save registers. So the one thing that I've found out as I've been pondering all this code is I've figured out, if we go to the beginning of what appears to be this function, we see this instruction here. And it is moving basically all of these registers into the stack. Fun fact, SP is actually just 5EA0. Let's branch to that address. There it is. Here it says A7. Here it says stack pointer. Those are actually the same thing. It's a stack pointer, just another name for A7 because the A7 register has the job of being a stack pointer. I don't know if it has any special abilities or if that's just a convention, but there you have it. A7 is used as the stack pointer. And you can save you can move multiple registers by listing them out. Here you can see that they're listed out as ranges. Here you can see they're listed out one at a time, but it's the same thing. And that's pushing these onto the stack. So this function is definitely saving register state so that they don't get clobbered. But this function here doesn't save anything. So I'm very interested as to why it's not saving it. Maybe it's not a true function. It's just a subroutine. It seems to be, I think these are the things that actually call into this function. So interesting. It's being called from many places. the keyboard or the gamepad polling. So we could actually rename this. Let's see if we edit function. So I could call this poll gamepads. And there you go. And then everywhere where this is actually called from, it will have this pretty name instead of just the number. So I think if I could probably double click this here. Let me try double clicking. And yeah, we can see here from this function here, we are calling poll gamepads. So yeah, very nice. So this is going to make our life easier as we start figuring out routines. We can name functions. We can define, or we could add labels to stuff. It's good stuff. Now, I believe we could also use this to compile. So we could take this listing and we could assemble it back into a binary file and use that as the ROM. So we could maybe edit some of these instructions, assemble it, and it should work, but I'm not 100% sure that if we took this as is and assembled it, if we would get the exact same binary as we put into it. All right, let's do a little science here. Let's export program as a binary, and size seems to be good. Still added the .bin, whatever, it doesn't matter. Let's just get rid of that. Just for my OCD. Yeah, fine. Okay, so we're gonna open a git bash in here, and we're gonna go diff. I don't know why it's big like that. Diff wotis.md wotis rtmd. Okay, it says they're fine. This is great, because what that means is that I should be able to now, when I want to write my patch, I can edit the instructions, and it should just work. Like for example, I could go into here, and let me see here, patch instruction, and then I could type in tst dot. Let's do move q, and then hash 0x0d0. And yeah, it'll just write over those bytes and everything. Because there's no option to, well, first of all, there's no option to do that in the main debugger. You can't input assembly mnemonics and have it insert them. So you'd have to do it byte by byte with the machine language, and that it would be very annoying. So it's nicer to have an assembler, and instead of having to do the assembler and then copy the bytes into the emulator, it's nice if I could just assemble and then generate a new binary that I could use for that purposes. Anyways, so cool. So we can use this as our assembler, as our note taker, as we understand more about the different functions and routines, and everything is going to be good. Let me undo this. There we go. We have Control Z support, which is always nice. All right, so now what I want to do is I want to go back to where we left off, and I want to try to figure out the combat game logic. Dice roll, detecting or determining whether you hit someone with a melee attack. So we had found a very nice place to start there, and that was, let me see here. Oh, very nice. So the function that I labeled, it shows up in here, poll gamepads. I can maybe rename this one. Yeah, so we want to figure out the attack logic. So let's go 1430C. If we could add a comment to here if we wanted. I don't know what the... Interesting. Semicolon allows us to set a comment, and so we could put in here. So now we've added a little sauce to it. We say, yeah, we load the strength stat here. Do table lookup for strength accuracy bonus. Boom. All right. So yeah, now we can start labeling stuff as we see fit. All right. So assuming this is all one function, we scroll up far enough, we should be able to get to the beginning of the function, which might be the actual calculation for attacking. It might be all the attacking. It might only be detecting whether a hit was happening. I don't know, but let's tentatively call this one do attack logic. We still don't know if it's only for melee, or if it's for also melee and ranged, or all sorts of things. If it's used for enemy attacks and character attacks, or if it's only for character attacks, we don't know yet. But that's fine. Okay, so what I want to do now is just see if this is actually the start of the whole thing here by setting a breakpoint in our emulator and seeing if it gets hit. Alright, here we are back in the wilds. And we have ourselves an encounter. Oh, this guy's way out there. Alright. Take your time. Let's do it. Alright, didn't hit the breakpoint. So that indicates that whatever it detected as a function there, that is not the entry point to that whole routine. Alright, so I'm just gonna undo that naming here because apparently that was premature. Maybe I should double check these things before I start to give them names, because that just don't seem to be it. So what we could do in this case is we could do a trace of what happens, and then from that trace work backwards to see how much of this code is actually part of, that operation. But we already have a trace, do we not? If I'm not mistaken, trace actions should be a trace of that stuff. So if I search for 1430C, certainly we do see it in here. We can work our way back up to where a subroutine was called. Yeah, because we see that we have this add B, and that is here. And here we jump to a subroutine, is returning from subroutine. So there was subroutine called a subroutine. But we can make our way back into this routine if we just keep scrolling up until we get to the 1427. So 1427E is also part of it. So 142. We go up, 27E. All right, so this is part of it. This has a label associated with, so something's jumping here from 13CO4. All right, so this is interesting. We are actually jumping to here using the address stored in a register. So this is a more dynamic. It's not entirely apparent from the code. Just looking at the instructions that you would jump to here, you have to know what's in that register, which makes things more interesting. And we can see here, we load an address into here, and then we use that address to load another address into here. So we're doing some kind of a dispatch lookup table here that could be part of some kind of like a case, switch case kind of deal. But this is going to make life a little more difficult, I believe. But yeah, we get here from 13A. Yeah, so if we follow this down, we should find a branch that uses the register. Yeah, so because the disassembler doesn't have any information about what is really in this A0 register, it can't tell us where this is going. References, add, edit. Well, the reference type is computed call to address. And let's just add this one in here, see what it does. 1427E. 1427E. Then it says, yeah, we're going to jump to this subroutine, and we double click on there, and how it has a reference to where we come from. So maybe if we double click here, yeah. I mean, we could add these, so as we actually look at the trace and we understand where these like computed calls actually go to at runtime, we can annotate that information into here in a way that it's not just a comment, it's actually encoded in a way that this machinery can understand. It is nice that it detects these like data tables and stuff like that and shows them to you. So this is a really big table offset. So it would be interesting to understand how the lookup into this table is computed, what stats, what things is it looking at? And that would maybe give us a hint as to what all these different labels mean. Like they're all in the same area. So this is definitely all combat logic sections, branches, whatever you want to call it. But yeah, you could basically look at this as like just one big switch. And we are switching D2. So whatever is in D2 is controlling how we look up into that table. So let's set a breakpoint here and just see if this is one that always gets called during combat or if it's only sometimes. I feel like this one probably will always be hit. But then there's going to be a lot of branching down there. I don't know. We'll see. So 13AE0. All right. So your ass is kind of stuck here. Can you hit my mans? No, maybe. Maybe. Nope, you can't hit him. Okay, well, it sucks to be you. What if we go up here? All right, you're just useless. Fair enough. How about you? Ah, you can do something. All right, so we do this. Now I think we should hit a breakpoint here. What do you guys think? Yeah, we hit the breakpoint, and that happens after the animation. So this is still after that animation is triggered. Yeah, so here we see a value is being loaded from memory into D2. Now, I think this shift is to turn it into addresses tables because, you know, those are probably 4-byte addresses in that table. So it's got to multiply by 4, the table offset in bytes. And then we load the table. We move a value from that lookup table. Well, that's it. We move an address, and then we jump to that address. So it would be interesting to know what is in A2? What is this address A2? Which is 3EBF6. And I think our static disassembly would probably tell us more about that. So where do we load A2? Here with this. And this is interesting here. I figured this out a little while back when I was looking into stuff. But if you look here, this is a 16-bit address. So this is a move byte. The address supplied is supplied within the instruction stream. You see A4CE, A4CE. But it's moving to FFFF A4CE, but there's no FF in here. So A4CE would be an address in the ROM. You can't write to that generally, except maybe a little bit of battery backup, but that's not what this is. This is writing into the RAM, which is at the very top of the memory space, or like the highest address. So if you look at the memory space here, you see that the actual RAM connected to the CPU is at FF0 to FFF. The top 8 bytes don't matter because it's a 24-bit address bus. So here, this is writing to RAM. And you might be wondering, but it doesn't, like, where does the FF come from? And it's actually, it does sign extension when you give it a 16-bit address. So if the top bit is set, which it is for A, then it is going to sign extend and you get FFs in the top. So you can supply a 16-bit address to get at the very top. But it's interesting because you can only get half of the RAM using a 16-bit address. You can get the bottom half. But if you wanted to get, for example, FF0000, if you put 0000 in here, it would not get sign extended, and so you would get the very beginning of the ROM. So you can use 16-bit addresses by themselves to get the very end of the RAM or the very beginning of the ROM. Entirely apparent just looking at it. So what we're doing is we're storing whatever is in the address pointed to by A2. We're storing that value, that byte, into RAM. We're incrementing the address by 9. Yeah, because load effective address, it puts these brackets in here, but that doesn't mean it's actually accessing RAM. That's just to trip you up a little bit, to keep you on your toes. So this is not a RAM access. So we load the value at A2 into this memory space. And then we move up by 9 bytes. And then we compare something at another memory location with 0, 1. All right, so we're back here on our bullshit. We changed our breakpoint. Let's try again. Okay, I changed my character ended their turn, but we got the same turn again. So here we go. And there we go. We're in here. So now we're at a breakpoint at the very beginning of that function. And it looks to be a true function. So nice. And so we can see A2, when we come in here, it contains 3EA2C. So let's look into that. You know, at this point, I would love to actually have a trace and see where they actually loaded A2. I wonder, I could search 13AC2. 13AC2. That's not a 3. You can't see it because I'm typing. It's on the other screen here. There it is. There's where we branch to it, but there it is here. Move B. So where do we load? Here we're moving into the memory, but now we're comparing with them what's at A2. Interesting. Where do we actually load A2 is where I would, that's where I would be most interested in learning about. Where is A2? I lost it. I lost the plot here. A2. Okay, we've highlighted it. Do a comparison. Here we're moving some stack into A2. We got lots of loops here. So A2 is being set sometime in the distant past. Here we're adding load. Okay, so here's the start, I think. This is the inception. So 1371E. All right, here's probably where A2 is being set originally, and it has created for us a data label. So there's data in these hills, and it's being referenced by a whole bunch of places. And this part is also being referenced by a whole bunch, but this is like probably a lookup or something. So lots of zeros in here, FF 10, FF 000, and then some stuff. Right, because some of these might even be addresses too, so it might be like 00FF10, I don't know. It's hard to say exactly what this is, but this looks like some kind of funky data for sure. Maybe. I don't know. Okay, so we have at least learned where it originates from. So is this function the function that's the start of the gamey calculations? I don't know, man. 1371C. Let's put a breakpoint there. All right, this does not seem to be the sauce, because whenever I press any button, this is getting hit. So this might be something to do with animation, because look, when I press down, it's gonna load. So this A2, this table, this data that we're loading in here might have to do with like frames of animation. Because yeah, I'm hitting it like a bunch of times, and then we move. All right, so we've maybe gone a little too deep. Let me just disable that breakpoint for a second, and we'll just keep going here. We're gonna take a little walk. No, we don't have to take a walk here. And then we re-enable the break. Oh no, I hid my, never mind. I'll just go like here, like that. F12. And now if I do my attack. Okay, so no animation happened, but then once I click in here, oh, but it did that animation before it hit this one. And this one isn't even gonna do an animation, right? Like, yeah, I don't know, man. That is weird, but at any rate, certainly we know that even when we're not doing any sort of gamey stuff, we're just pressing buttons, it's getting tripped. So this can't be what we are interested in. We've gone a little too deep. All right, well, we'll trace our way back a little bit to here. This one seems to be like it's a good candidate for the start of attack logic. Yeah, maybe do attack logic. We'll just rename that one there. So I'm curious as to whether this is also used for when the enemies attack. I would assume maybe yes, but you never know. So we'll do an attack here. Break after the attack animation. We can continue. And yeah, when the enemy attacks me, we break at the same address. So that's one little piece of intel. All right, well, let's just do a little mapping here. We'll see where we can get from this starting point. Let's rename this one to like attack jump table, blah, because that's sort of what it seems to be. Good. We're just marking things off here, taking notes. But yeah, we go to that jump table. I wonder if this is hit for any sort of action. So like not just attacks, but also like casting a spell or something. And this jump table is to figure out what you're actually doing. That's a thing that could exist, right? So in that case, A2 would be like the class of action that you're taking, maybe. And so we go to 1427E here, which is not considered a function. It's just a subroutine. Yeah, maybe do attack logic is going here, and something else also might jump here inside this whole thing. Now I wonder if anything, how this links up to. Yeah, that links up to here. So this is now the stuff that's doing all the calculations. So this subroutine could be possibly a subroutine that this is for a melee attack. So let's put this one here. Try an action that isn't a melee attack and see if it hits my first breakpoint. Yes. There you go. It hit this one. So this breakpoint here isn't just for attack. It is for spells as well, probably other things, and I would bet you anything that what's in A2 here is in fact ya boy, the type of action. So if we look at what A2 is right now, 3E81C, which is, I'm sure that's different than what we had with our melee attack. I mean, maybe it's exactly the same. I don't know. Okay, well, let's try the action of just hiding. Okay, hiding did not hit my breakpoint. Interesting. All right, hit me. Here we are. Okay, we are back in business. And A2 has 3EA2C, which is what... Yeah, I figured it was different. Melee is much different than magic missile, right? Let me just make sure I copied that in right. 3EA2C. Yeah. Way fairly later down in the table for melee than for magic missile. Okay. So some actions that you take are dispatched in this table here, and other ones go to a different thing than this function altogether. Interesting. So this isn't really the action pointer itself. It's like I don't know what it is. Derives action pointer. And then, yeah, magic missile gives us this one. Melee gives us this one. There might be another one for ranged attacks. Who knows? But yeah, I think the next steps here is I think we should just focus on this melee logic subroutine here and see if we can determine what things feed into it. Obviously, A4 feeds into it. Anything else feeds into it. We can make note of those and just kind of step through it. See what calculations are being done and take it from there. I mean, we already have one piece of intel on this, and that is that this is the strength bonus for doing accuracy, but I mean, I'm sure there's more insights to be gained. Honestly, now that I'm thinking about it, I wouldn't be surprised if A4 is a pointer into the targets character sheet here. But anyways, yeah, I've made some progress here. We're working at it. We're chipping her away, but I need to take a break here. So I will see you again when I see you with some more of this bullshit.